Hello, I'm Robert, and sorry the last one got cut off. My camera has a maximum of 30 minutes. So now I'm going to continue talking about this idea of sending a hammock to a space station in order to deal with the problems of zero gravity. So to explain how this works, well, imagine it was inside one of the ISS modules towards one end, so it is not getting in everyone's way. And then let's call the four sides of it, they're normally squared off on the inside. So call the four sides the floor, ceiling, and the left and the right hand walls. Then the way I imagine it working is you would have a motor in the middle of the floor. Directly opposite, you have a motor in the middle of the ceiling. And you don't need to have anything between the two. You don't need to have any kind of axle between the two, because if you just have the pivots at the top and bottom, that would be fine, and it would leave plenty of space so you can actually walk through it very easily when it's not in use. Then the way the rest of it I imagine working, there are two ways you can put your hammock. And one way is so that you're parallel to the axis. So that would be you're orientated, say, vertically with your head up, your feet down, and going round and round, just like in the Gravitron amusement park ride. And then the other way you could be is that you have your feet and your head lying horizontally, so your head follows your feet, going round and round in circles. And if you're lying that way around, then you might have to curve your feet up, and so lift your feet up and lift your head up, very much like you are in a hammock, in order to keep a kind of constant distance from the centre. So you don't run into obstacles if you're very restricted in space. In the other direction, then it doesn't really matter, so long as you have a flat edge to your habitat. So then, getting down to the details, well, first of all, use some very lightweight, very strong material. I imagine the best grade of carbon fibre, such as in the Olympics, the sort of material they use for making Olympic bicycles for the velodrome. And instead of being attached just using ropes, you obviously have to be attached with something rigid, so that the motor in the centre can move your hammock around. However, you're not talking about something enormously strong. It doesn't matter if it's a little bit flexible or whatever, because only a little bit of force is needed. It's like when you spin a bicycle around, and it just keeps spinning. And if you had just a very, very gentle force on the axle of a bicycle, you could, on a bicycle wheel I'm talking about, if you just gradually set it spinning, it would spin faster and faster and faster, and then it would stay spinning for quite a long time. You just need a little bit of a gentle force to keep it going. And these motors, the top and bottom, I imagine the best would be kind of electric motors decoupled from the actual thing that it's driving. So the advantage there is that if you were to stop, remember they're not travelling at very fast speed, they're only travelling at a comfortable jogging speed, and suppose the astronaut puts out a hand, they just kind of stop themselves as they're going around. Then you don't want the motor to keep driving them around. And so the motor would be designed so it stops very easily, however it is that you do it. And indeed it might actually help if the motor actually assists stopping. So if you just reach out and touch something, it would instantly stop at comfortable braking speed, braking acceleration. So that's some of the most important details. There's one other detail, which is the actual spinning motion of the... whenever you're spinning around one way, as the motor accelerates you to go faster and faster one way, it's actually accelerating the ISS itself the other way, because we're in zero gravity. However, the ISS obviously doesn't spin very quickly, because it's so very big and so very heavy. Technically, it's the moment of inertia of the ISS about your axis would be far, far greater than your moment of inertia. Nevertheless, if you keep spinning around for hours on end, and for as long as you're spinning, the ISS is very, very slowly turning the other way, and after you spin thousands of times around that way, the ISS might move a little bit in the other direction. So then you need to think, what's the effect on the attitude of the ISS? Well, as it turns out, the ISS has got big, heavy flywheels, which it uses for attitude control. So the simplest solution there might be simply to couple your motors to the ISS, maybe through a network or whatever, so that it just starts spinning whatever is necessary in the attitude control. It just compensates. And the other possibility is that you might have flywheels. So you have a flywheel at the top and bottom, or just at the bottom. And so I leave that to the engineering details, possibly a large radius flywheel, a small one obviously enclosed because it would spin much faster than the thing that you're spinning in. And then another minor detail of the construction is that I envisaged it with that some people might be quite happy seeing the kind of blurry effect of the spinning surroundings, or when you're going at slow spin rates, but you might want to be enclosed, very much like the Graviton amusement park rides. So in that situation, then you want some kind of cloth, like a shower curtain, that goes all the way around the thing, or possibly something that actually spins with it. So that again would be an engineering detail and technical detail to look into. And I think as far as the actual design, that's about it. I think it's quite important to have both directions, so you're not just vertical that way, but that way, because they will have different effects on the body. So if you are parallel to the axis, then your horizontal canals will be stimulated and feel like you're spinning. If you are perpendicular to it, then your vertical canals in both ears will be stimulated. And it will be very interesting indeed to see who adapts better. That if you have been pre-adapted to spinning motions on the Earth, so either that you were an ice skater when you were young, or a whirling dervish for that matter, or if you did some pre-adaptation exercises like the MIT experiments, where you spent a few days doing 1 hour a day in a centrifuge on the Earth, will that help you in space? And that might help you better. You might think intuitively, but experiments often prove your intuition wrong. But it might be that if you go and are parallel to the axis, because your horizontal canals are stimulated, then maybe pre-adaptation will work best for that. And then the other way around, because the vertical canals are stimulated, then maybe that would be better if you got experience of tumbling while skydiving, or experience of sailing in very rough seas. So it'd be very interesting to see if that does pre-adapt you to artificial gravity, and who it is who finds it easiest, and who it is who's very susceptible to it. Now, this leads to something which is going to be a little bit of a problem with all this, is the NASA guidelines and their attitude to medical records. You can go and look it up on their website. They will not release individual astronaut medical records until they die. So they only provide aggregate medical information about their astronauts. This could be a bit of a problem, because you would then be relying on only members of NASA would be able to analyse the data, and then they would provide it as aggregate information about their astronauts. And really, you want everyone to be able to look at the raw data, and the medical researchers, they might want to slice it in different directions and look and find new things in the data. So then the question is there any way around that? And also you might want to correlate. So if you find someone is very tolerant of it, then you might want to say, were they a sailor, or were they an ice skater? Did they do pre-adaptation in a centrifuge? Does that help? So all these sorts of things, you want to identify individual astronauts in the data as well, and see what effect that had. And you want to know things like their resting heartbeat on the Earth, and their resting heartbeat in the ISS, and their red blood cell count, and other bits of information. So I don't know if there's a possible way around that. Maybe some way by which the astronauts would sign a medical release form saying they release any medical data that is collected during the experiment, plus relevant medical data that is also outside of the experiment, if it's relevant to the experiment. And then optionally, if someone didn't want to, then they could not release that. So that might be a possibility. And then in the worst case, well, you do at least get the aggregate information from NASA, and then you have the Russian cosmonauts, and they don't have the same regulations. So the Russian cosmonauts can very easily release their own medical data. There's no problems with that. So in the worst case situation, you've still got the aggregate data from NASA, and you've got individual data from Russian cosmonauts, and quite probably from other countries as well, who don't have the same regulations that NASA has. So, anyway, it could be very useful. So you have lots of astronauts going back and forth from the ISS, and over a long period of time, you get a lot of medical data. And so there's lots of things we can find out here. And this is going to be a very useful experiment. And I think this is, you don't need to kind of pitch this, saying this is going to help the astronauts. It might do, very hopefully it will. And it's quite promising it will. But whatever you discover will be very useful medical information that will guide us. And it could set us back to the drawing board either way. So it might turn out that human beings are very sensitive to this, more sensitive than they are on Earth. It doesn't seem very likely, but you've got to bear in mind as a possibility. The only data we know for sure that some astronauts can tolerate 12 rotations per minute and for half a minute. Because it wasn't an actual experiment, but the Skylab astronaut jogging around on the inside, and they just jogged around for half a minute and they stopped, and they didn't have nausea, and they didn't seem to be dizzy or anything like that. So that is about the only data point we have. But that is enough to suggest that in this short-term centrifuge, at least you'll be able to do, and I would imagine probably some minutes at least, of these 12 rotations per minute. And from the experiments of the Earth, I'd be very surprised if there aren't at least some people who can tolerate 30 rotations per minute for an hour or so, and possibly for longer. But whichever way, then the other medical thing that we can discover in space is the effect of low gravity. So we know that in zero gravity you get continual bone loss. And we suspect that in zero gravity you have a maximum lifespan of perhaps less than 2 years because of the accumulating effect of all the medical issues. And because astronauts do in fact become ill if you're a very long time in space. So the question then is, zero gravity, say your lifespan is 2 years. We don't actually know because nobody's actually died, obviously, in space. You can bring them back to Earth if they're sick. But suppose the lifespan is 2 years in space before you have to return to Earth in zero gravity. And obviously people can live over 100 on Earth under normal gravity. But what about low gravity? Well, maybe it's somewhere in between the two. Now, if your lifespan in lunar or Mars gravity is, say, 10 years, for instance, then that could be quite a serious issue if you're thinking of possibly living long term in those situations. And then there's also the problem that when you're in zero gravity, you continually lose muscle mass. You continually lose, both your muscles and your bone loss. You continue your bone loss. And when you are in Earth normal gravity, then your bones are kept the same amount. And then the question would be, does this have any effect on growing children, for instance? Will bones grow normally under low gravity? And I don't think anyone knows. If you're optimistic, then you say that the body will just adjust to low gravity because it's only losing mass it doesn't need. And so long as you don't want to return to ordinary gravity, then all is fine. But that's just a hypothesis. And it might very well be that in low gravity, you just keep on losing mass. And the bone mass just goes down and down and down. Does it stabilize? So far we haven't had astronauts in space long enough to know if it does stabilize. So these are all things that we can find out in evidence of low gravity. Personally, I'm interested in low gravity both for colonies on the moon and settlements, which I think, if you've seen my article, I don't think colonization, going to space to colonize, I don't see that as being a very useful way of proceeding at present. because you can always build homes much more easily on the Earth than anywhere in space. But going into space to set up science research stations, then you might well want places where people live even very long term on the Moon. And then on Mars, well, personally, as you may know from my other talks and articles, I don't think we should send anybody to the surface of Mars because of the great risk of contaminating it with Earth life. But if you're in orbit around Mars and you're exploring the surface with avatars on the surface, first of all robots and more sophisticated avatars, you might well want to be able to use them in a simulation of Mars gravity. So you might actually be living in a habitat that is permanently in Mars gravity. So I'm quite interested personally in the effect of low gravity on the body as well. I was going to talk about interplanetary, preparing for interplanetary flight, but I'm not sure that there'll be enough time on this video. I think I'll stop it now, and then I can maybe talk a little bit more about that.